Okay, welcome. Today's lecture or presentation, if you like, I'm just going to work through the first assignment for exercise physiology, which is P1, P2, M1. I'll show the grading criteria that we're going to work towards, and then we'll just crack on. So I think there's about 13 or 14 slides. I'm trying to sort of follow the format of your assignments, so it's useful to sort of pause the presentation perhaps as you're completing your assignments, but you'll also get the sort of slides and what have you sent to you. So the thing we're working towards is this. So describe the musculoskeletal and energy system response to acute exercise, and describe cardiovascular and respiratory system responses to acute exercise. Explain the response. So the key thing here is the response in the short term. So I think it's useful to kind of look at it from a perspective of saying what is happening to these systems as we move into exercise. So during the warm-up, during the exercise session, and then the adaptations to that exercise is what comes later. So just to make sure that's very clear, we're dealing with exercise in the short term. So the section you're asked to describe first is musculoskeletal responses to exercise, and I've put it under these four categories. So increased blood supply to the muscles, increased pliability, increased range of movement, and muscle fiber tear. So you have to discuss each one of these fairly briefly, but I'm going to just sort of go through that quickly with you. So the first one is this concept of increased blood supply to muscles. Now, if you think we have 5 or 6 litres of blood in our body, it's not that much when you think about it. So as we sort of sit here now, hopefully quite relaxed, our blood is being used a lot in our digestive system. So it's doing it sort of digesting nutrients, moving food along through the gut, kind of looking after our sort of resting and repairing functions, our immune systems and the like. Now, when we exercise, we kind of increase the demand for blood in our muscles massively. So our sort of heart rate can raise from 50 or 60 beats per minute to somewhere near 200. We can increase our total cardiac output by about 4 or 5 times. It can be pretty massive. So something has to open up in the muscles to allow that blood to bring its nutrients. So one of the key things that happens when we start exercising is blood flow increases to those muscles. Now, to do that, really a couple of things are responsible. So on this picture on the right hand side, what I've tried is quite from a slightly more complex book, but I'll sort of just try and sort of highlight a couple of important points. Where that's not a particularly great colour. Where we see here, nor is that. Let's go for red. There we are. So here, what it's trying to show is that decreased pH, i.e., so acidity. When acidity is raised, one of the things that happens is it causes an increase in the diameter of blood vessels. So where blood vessels are, when we start exercising, particularly when we start warming up, let's say we're going for a jog, our muscles in our legs start to be used. Now, as a byproduct of that contraction, we get released these what are called metabolites. So things get released into the bloodstream at those muscles that are being used. It causes the blood vessels to relax, so it allows blood flow to increase into them. The other thing that happens, and I've got this on the bottom picture here, is where blood vessels are stretched, they release something called nitrous oxide. Nitrous oxide, or nitric oxide, sorry, not nitrous oxide. Nitric oxide is a powerful vasodilator. So the stretch on the blood vessels causes them to dilate. allowing more blood into those muscles. As we go to number 2, this increased muscle pliability. So when we exercise, we start to create heat. That heat seems to sort of warm through the muscle, warm through the connective tissues, and it allows them to stretch that little bit further. When we exercise, our nervous system seems to create a sort of relaxation of muscles as well. It allows them to kind of let go to a certain extent. So it allows the range of movement to be increased, particularly if we go through a full warm-up that takes our muscles through their full range of movement. This number 4, increased muscle fiber tears. So this is a bit of a weird one actually. I've put a couple of things of note on the side here. On the little picture in the middle, this thing here I'm just outlining. So this is a muscle fiber. We looked at the structure of muscle fibers in anatomy. When we look at this thing here, this is a sarcomere. So this is a, let's try and put it, sarcomere. Now what we can see is if we can see here, I'm just outlining where Z lines are. So what we have is we have these myosin filaments in the middle, and they're kind of anchored by those Z lines either side. So if we see, I'll just cover it in red here, these are the Z lines. They anchor the actin, and so it allows the myosin filament to pull that actin close together. Now in exercise, particularly where it's eccentric, where there's a real sort of pulling apart of muscle, those Z discs get torn. And it's one of the things that is potentially a stimulus for hypertrophy. It's definitely associated with that soreness that you get post-exercise. So you get tiny tears in those little Z discs, and the idea is that when the muscle sort of repairs, they grow back stronger, potentially. So exercise sort of creates these tiny little tears, but it's that little tearing, the little inflammation you get after that, which gives that pain, that soreness that you get maybe the day after exercise or even 2 days after exercise. We call it delayed onset muscle soreness. It's called DOMS. So as we move through this picture, we're going to return to later. This is one of the cardiovascular responses to exercise. If I just sort of go through it quickly, I'll go through it in a little bit more depth later on. Now, what we have at the bottom here, we have someone who's resting. Now, if you look at their resting, their cardiac output is 5 litres per minute. So if you can imagine, let's say my heart rate was 70 beats a minute, and every beat I was beating roughly 70 millilitres of blood per heartbeat. So that's around 4.9 litres per minute. So that's a sort of fairly standard amount of blood flowing out of my heart per minute. It doesn't seem that much really, does it, when you think about it? A couple of big bottles of Coke. Now, what we've got at the top is someone who's exercising heavily. So this person's playing squash, so lots of so heart rate raises. So if we think of a resting heart rate, and the bottom was about 70, at the top we could sort of go somewhere north of 180. The other thing that happens when you start exercising is your stroke volume increases. So this is the amount of blood ejected within each heartbeat. So here, her cardiac output has gone up to 25 litres per minute. So 5 times as much as being at rest. Now, what we see is that at the bottom, when she was resting, 25% of her blood was going to the digestive tract, and only, let's say, 15 to 20% going to the muscle. If you look at what happens when we exercise, I'm going to pop it in purple. Now, only 3 to 5% of blood is going to that digestive system, but actually now 85% of that is going to the muscle. So as we exercise, our body kind of shuts down blood vessels going to the digestive tract, and the muscles working opens up blood vessels going to the working muscles to allow them to receive that increased blood flow. So just having a look at what we've kind of covered so far. I've only gone 10 minutes in, but it's just useful to have a look at these lead-in phrases so you can just get an idea about how you're sort of working, about how you're going to articulate these ideas. So let's just trace this through. So we're kind of looking for an introduction. So as the body moves from a non-exercising state into a warm-up, a number of responses occur. So you could suggest something like a number of responses occur to allow us to meet the demands of increased exercise intensity. You could say a number of responses occur within the cardiovascular, respiratory, musculoskeletal and energy systems to allow us to meet the demands of exercise. It's your call. You then move on, you say the increased work done by muscles requires a greater supply of, and you come up with something. So you could say the increased work done by muscles requires a greater supply of blood, which brings with it additional oxygen and nutrients to supply working muscles. Number 3, to meet the demand for oxygenating blood, the blood vessels, well, again, you choose. So you could say the blood vessels need to expand to receive more oxygenated blood. This is a process called vasodilation. Number 4, the increased muscular activity creates additional heat. This seems to create a relaxation of the muscle tissue, partly due to connective tissues sort of loosening, but also allows this sort of neural relaxation as the brain allows the muscles to stretch that little bit further. So taking their muscles through a full range during warm-up helps us improve muscle pliability and increase their range of movement. At the bottom, during exercise, particularly where it is intense, that should say, or involves eccentric contractions, muscles can tear. So remember, they sort of create these tiny little tears in the Z discs, which might cause minute bits of inflammation. This is often a good stimulus for the muscles to use to grow back stronger, but also can be the cause of that sort of muscle soreness. So you might finish by just saying this warming of muscles allows us to arrive at exercise after a warm-up, prepared and ready to go. It could reduce the risk of injury and increase the performance that we get. So we're going to move into the different bits. So it asks also for energy system responses, and you need to cover these 4 things. You need to mention phosphocreatine system, the lactic acid system, the aerobic system, this concept of the aerobic energy continuum, and also make mention of energy requirements of different sports. So again, a lot of this was covered in anatomy. So we should have a fair grasp of these first 3 systems, but it's important that you do give a quick recap of them as you move into your work. So remember, the phosphocreatine system is that system that's responsible for very high intensity exercise. So it will predominate in something like, let's say, a 60 or 100 meter sprint. It provides all-out intense energy for all-out intense activity, but it's very, very limited. The fuel is phosphocreatine. It's a sort of high intensity exercise. The lactic acid system is also a high intensity system. It's brought in at different levels though, to a certain extent. So I'm going to talk you through this sort of continuum in a minute, but I think it's important to think with a lactic acid system, we present it as something like it's always used in the 400 meter race. A 400 meter race is a perfect example of the lactic acid system being used. Well, in that 400 meter race, you may start by using that phosphocreatine system. So the phosphocreatine system will provide some energy, but also in the background there's a little bit of aerobic energy, but the lactic acid system becomes really important. So during that race you might sort of say, actually the aerobic system never shuts off, so that's got to have a little contribution. As we get off the line, we use the phosphocreatine system to sort of get us running, and then the lactic acid system has to supplement the aerobic system to sort of provide that additional energy. And the aerobic system, number 3, is always working. It's never switched off. So as we're sitting here now, we're using our aerobic system, probably using a lot of fats, a little bit of glycogen. But if we start moving, let's say I sort of take my dog for a walk or whatever, just a nice flat walk, very sort of, fats are a very sort of large energy source during that. But if we then go up a hill, a little bit more hard work, we might start to use slightly more glycogen and glucose as energy sources. So again, the aerobic system can work at different intensities, but when it's not able to meet the requirements of that exercise intensity, the lactic acid system provides that little addition. So I'm going to talk you through these key points, and this is how you should really sort of present your explanation of energy system responses to exercise. So number 1, all 3 energy systems work to create ATP, and we looked at this in anatomy, adenosine triphosphate, and that releases its energy from muscles by breaking its bonds and energy being transferred into the muscle fibre. So we have 3 systems used that either create or reform ATP. So wherever we eat food, let's say we're eating carbohydrate, protein or fat, essentially what we're doing is we're sort of fueling our energy systems to create ATP, adenosine triphosphate. Now, if we look at this 5 points that I want you to make, you have to get these across in your writing. Number 1, at rest our ATP stores are high and we are using our aerobic system. So this is what I described before. And we can sort of have a look at this picture on the top right here that I'm going to just underline there. Now, at a very low exercise intensity here, can you see how as a total contribution of my energy, fats are very high? So fat is using quite a large is a large percentage of my energy use. So that's an important thing. You can see as exercise intensity increases, so as it moves in this direction, I think I just want to get something across. So carbohydrate, this one in blue, I'll use my marker in blue there. As we increase exercise intensity, the use of carbohydrate goes up quite markedly. What looks a little bit like what's happening here, so we sort of see fat, it kind of looks like it's going down. Now I think that's a little bit misleading in some ways. The actual total amount of fat we use continues to increase, so it's going to keep going up and up and up and up, but the amount of glucose we're using, sorry, carbohydrate we're using, increases really much more. So actually as a percentage of our total energy use, fat goes down, but the actual total amount of fat we're using continues to increase. So point number 2 is as exercise intensity increases, our use of fat increases, but not as much as our use of glucose and glycogen. As exercise intensity increases further, we will start to use the lactic acid system to supplement the aerobic system. So it's kind of like a little turbo, if you like, as you start to sort of max out. Aerobic system is quite slow, it's very efficient, so you need a little bit of an extra boost. When bursts of high intensity exercise are needed, the importance of lactic acid system increases to meet the high demands for ATP. And then at the bottom, when maximal intensity bursts are needed, the ATP-PC system is drawn in to produce instant energy. So this is that sort of instant uncoupling of phosphocreatine. It splits, adds a phosphate to ADP, and immediately reforms ATP. So you need to describe this concept of a continuum. Now, if we look at these pictures on the right-hand side, let me just take a red. Now, what we see here is that a marathon can be seen as an almost entirely aerobic activity. Now, people will have their lactic acid levels assessed at the end of a marathon, and they're often very low because it's a very aerobic exercise. Pain that people are feeling at the end of a marathon is often, it's much more about muscle damage. It's a very aerobic activity. Very little lactic acid gets produced. Now, if you compare that with, say, let's say an 800-meter run, it sort of grades it at around 40% aerobic, with the other 60% being anaerobic. So that sort of fits, doesn't it, really? Your aerobic system doesn't switch off. People who are very aerobically fit are generally pretty good at the 800-meter race. But there is a real sort of, that is a grueling race. At the end of that, if you look at the sort of current world record, it's, I mean, I couldn't keep up with them for 100 meters. For me, that was an all-out, beyond a maximal sprint for me. So someone doing that for 2 laps is putting a tremendous demand on their lactic acid system, a real sort of burning of that muscle, huge amounts of lactic acid created, but also there's still a contribution from that aerobic system. If you look at, say, at the entire other end of that spectrum, weightlifting, to lift a weight, it might take a second or 2, so it's entirely unaerobic. So that person doesn't need an aerobic system. There's just no, it may help in their training in order to sort of keep training for longer, to recover more quickly. But it's much sort of lower intent, or sort of not lower intensity. It's a high intensity exercise, but a lower demand on the aerobic system. So when we think about this, it's an odd thing, and I'm going to just sort of talk through my feelings about this, explaining it as a continuum. Is that it doesn't work as if we first use our ATP-PC system, then we use our lactic acid system, then we use our aerobic system. All of the systems are working at are working in varying degrees depending on the exercise, your level of fitness, and the intensity that you're working at. So the aerobic system is always working in the background. So on this picture on the left-hand side, it mentions this, what's called the base rate. Well, I think it's a really nice thing to include. So what we start with at the top left is we start with ATP stores that are high. So when we're not exercising, our ATP stores are very, very high. If we work maximally, for those first 10 seconds, I'm just trying to outline it here, our ATP-PC system will provide most of the energy. So if you trace that sort of peak ATP-PC system down, I'm just trying to sort of show here, there's a tiny little contribution of the aerobic system, there's a tiny little contribution of the lactic acid system, but in that first sort of 10 seconds of maximal intensity exercise, the ATP-PC system is dominant. Now, in exercise that goes to around 60 seconds of maximal intensity, the lactic acid system becomes the dominant energy source. But even then, at that sort of 60-second point, there's going to be some aerobic system involvement. So as exercise time increases, so we've got a 2-hour time here, the sort of dominance of those anaerobic systems becomes much, much less. So this sort of idea of a continuum of energy systems is a funny one to sort of try and explain. But what you're trying to show is this idea that the longer exercise is, the more drawn out an aerobic is, the less anaerobic contribution there is. In short-term exercises, so where you've got things like an 800 meter, 1500 meter, the dominant energy systems become much more anaerobic, but in the background there's still a little bit of aerobic work coming in. Okay, so we're moving now on to the section on cardiovascular responses, and again there's a few key terms that you need to get across, and I'm going to just try and go through them in sort of stages. So one of the things that is an important concept, I think, is this idea of a cardiovascular control center. So in our medulla, a part of our brain, we have a control center. Now, this will sort of process information. So in things that will sort of process, the two main things we've got here is, I'll cover them in green. So number one, we've got these things called, oh, I'll try and green. There we go, green. Is our baroreceptors. So baroreceptors monitor pressure. So if you think let's imagine you just lie down for 5 minutes. Your heart doesn't really have to pump uphill. It sort of has a very easy time. Now, if you're lying down and then you suddenly jump up, if you then have to sort of run upstairs or something like that, what you'll feel is that in that sort of moment where you've stood up, your heart rate suddenly has to go boom, 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 boom. And this is to meet the requirement of your brain for oxygenated blood. So baroreceptors, so measuring pressure in your arteries, they'll sort of experience, as you stand up, their pressure is suddenly going to drop. So they'll sort of think, blimey, if we don't get pressure back in that system, the brain's not going to have enough oxygen. So they report to the control center that pressure has dropped, and the control center creates a response to the heart to increase heart rate. So baroreceptors are one of the things that will inform our control center of a need to either increase or decrease heart rate. These are really key. So the brain has a control center called the medulla. It affects heart rate by hormones, so it releases adrenaline, and through the sympathetic nervous system, so it will kind of has nerves that will act directly on the heart. So even before exercise, heart rate increases as adrenaline is released. This is called the anticipatory rise. So this idea that you haven't created anything in your blood yet, but even before exercise, your heart rate begins to increase due to adrenaline. So hormones and nervous system control heart rate. Baroreceptors, what I described, monitor pressure. So when it drops, heart rate needs to increase to make sure there's adequate pressure to supply the brain with blood, and also the muscles with blood as well. Chemoreceptors, so down here we've got chemoreceptors, and they inform the control center about the chemical composition of blood. So this could be acidity, level of oxygen, level of carbon dioxide. So when things like acidity begin to raise, there's an increased need to circulate blood, and it causes heart rate to rise. The last thing we've got here is mechanoreceptors. So our mechanoreceptors monitor movement, so mechanical movement. So as muscles contract, relax, as limbs move, this again informs our control center that movement is happening and there's a need to increase heart rate. So all in all, what you've got here is this nice sort of picture, and the concept we need is that to meet the demands of exercise, our brain needs to know what's going on with the body, what activities it's doing, and how to respond accordingly. So it has three key things. baroreceptors monitor pressure, the pressure in the system. So when my limbs are moving and all my blood's being taken away, it's going to think, oh crikey, there's not enough blood left for my brain. So we're going to start having to beat much harder to make sure there's adequate blood to continue supplying my brain. Mechanoreceptors are going to monitor my movement and also tell my control center to increase heart rate, whilst chemoreceptors also are going to be monitoring the chemical composition of my blood, and when it becomes particularly acidic, for example, it causes heart rate to increase further. So you have to make a mention on cardiovascular responses, and again, this is blood distribution. This is what I described earlier. The key thing is that in order for blood to be available for working muscles, there has to be some redistribution. This is why you don't go for a swim just after you've eaten. If you've just eaten a big meal, all of your blood should be, or not all of it, a large amount of your blood needs to be in your digestive system, doing that digesting, doing that moving of food. If you have a nice roast dinner and then immediately go for a swim and start swimming as hard and as fast as you can, look how your blood wants to distribute. It wants very little blood in your digestive tract because it wants that blood available for your working muscles to keep you afloat, to keep you moving. So the problem is you've got those conflicting demands. So this is why you might be sick or you might be unwell if you go for a swim immediately after a meal. So blood redistribution is a really important concept, and it's part of why we have these kind of extended warm-ups as we're about to exercise. So one of the things that happens as we begin exercising, the metabolites in muscles start opening up blood vessels to allow more blood flow into those muscles, and we allow that shutting down of blood towards our digestive organs to limit flow to them and make it more available for our working muscles. So this is why sometimes if you just sort of go cold into a run, maybe after 2 or 3 minutes you start to feel like you're almost sort of cramping up. But if you sort of have a little run for a couple of minutes, do a little stretches, have another jog, gradually the distribution works more effectively and it opens up those blood vessels to your working muscles, shuts down the blood vessels to digestive tract, and you're sort of ready to go. So we move on to these cardiovascular responses, a couple here which are sort of fairly straightforward. I'll give you these pictures as part of your work. So on the left hand side we see changes in heart rate. What we see here is on the bottom of the graph we have increase in exercise intensity as working as a percentage of your VO2 max. So essentially what it's showing is there's a very sort of gradual, a very predictable increase in heart rate depending on the intensity that you're working at. So what you see here is heart rate increases in line with exercise intensity. Now on the right hand side what we see here is stroke volume. So stroke volume is the amount of blood that's ejected from the heart with each beat. Now what you can see, up to about 50% of VO2 max here, stroke volume increases in a very linear fashion. So what this means is as we start moving, as our limbs move, blood is sort of driven back to the heart more quickly, and it causes almost like a little stretch on the heart. Also the sort of action of adrenaline causes our heart to beat that little bit harder, that little bit sort of more it causes a stronger, more powerful contraction. Now, as we get above that level of exercise intensity, our stroke volume begins to plateau. So there's almost like a maximum amount that it can expand to. So at the bottom here, stroke volume that started around 70 begins to plateau around here, about 110. And then it sort of absolutely sort of maxes out about 115 milliliters. So this is partly because if you think beyond, let's say at those high intensity exercise, let's say my heart rate at maximum is let's say 180 beats. That's a heart that's got to beat 3 times a second. 1, 2, 3, 1, 2, 3, 1, 2, 3. And so each time it's got to fill with that amount of blood. So part of that sort of plateauing is possibly just the difficulty in filling that heart each time. But generally we describe stroke volume as being something that increases in line with exercise intensity up to around 50% of VO2 max and then begins to plateau. So here we need to just talk about blood pressure briefly. So blood pressure, remember, we have systolic pressure and diastolic pressure. So the diastolic pressure is the pressure in the system when the heart is relaxing, and the systolic pressure is the pressure in the system when the heart beats. So 2 important concepts. Now remember, cardiac output, stroke volume, plus or times heart rate is always going to increase. So as cardiac output increases, pressure, the systolic pressure, is going to rise. So what we see here on this picture is we've got 2 different types of exercise. One is related to the like an arm cycle, and one is a leg cycle. So let's just concentrate on the legs. Here's the diastolic pressure in the legs, and here's the systolic pressure in the leg. So this is the person going for a cycle. Now, during aerobic exercise, what we see is as exercise intensity increases, we can see this steady increase in systolic pressure. It's kind of what you'd expect, isn't it? What we see at the bottom is not a great increase. This is the diastolic pressure. The diastolic pressure is the pressure in the system when the heart is relaxing, when it's refilling. So the theory really is where we've got aerobic exercise, we don't see giant increases in that diastolic pressure because there's also there's not much resistance in the muscles. So where they're moving constantly, they're not resisting blood flow. So blood flow can get through quite nicely. It can come back very easily. So what we see here, cardiac output increases, causes systolic pressure to rise, but because there's very little peripheral resistance, the diastolic pressure rises, but not by that much. If we saw something like resistance training, we'd see a much greater rise in systolic pressure. So as we sort of strain, all the muscles constrict, we restrict blood flow through those constricted muscles. So the heart tries to work harder to push through them. So what we see is we see a massively increased systolic pressure, but also where we've got that resistance because of those constricted muscles, we see a rise in diastolic pressure too. So this is why in people with blood pressure problems, some resistance training exercises can be quite dangerous and advised against. So very high intensity, very powerful exercises sometimes cause large increases in systolic and diastolic pressure together. So you have to comment on this concept of vasodilation and vasoconstriction, which we mentioned before a little bit. So number 1, vasoconstriction is the constriction of blood vessels. So in you can sort of see the difference between these 2 blood vessels here on the right hand side. So vasoconstriction is where blood vessel will constrict. So for example, going to the digestive tract or even the sort of salivary glands will sort of constrict to sort of limit flow, limit blood availability to them. Vasodilation is really largely caused by muscle activity. So this is a real value of a warm-up. So the warm-up causes metabolites to be released, which causes a dilation of those blood vessels. So if we do a warm-up that's specific to the muscles that we're going to be using, it causes those muscles to dilate to allow more blood flow in. So part of that redistribution of blood. So just a couple of slides on respiratory, I think there's one slide on respiratory responses. So again, a bit like the cardiovascular system, we have a respiratory control center. So that takes information about our body and to a certain extent our mental state, and it creates a response which then makes an effect on our respiratory muscles. So we have another sort of anticipatory rise with our breathing. So if we, sometimes you might get it if you're, let's say if you're scared or if you're excited, you might notice your breathing rate rises. Now, nothing, there's no chemical change in your blood causing that to happen. It's almost like a sort of feed forward mechanism. So you can almost see this in this picture on the right. What we've got breathing response or ventilatory response at 3 different levels of exercise. So green is light, blue is moderate, and red is heavy. So all that's happened here is someone's been doing, so they're after exercise at a particular level, and their breathing rate and depth is monitored. So we're measuring how much air they take in and breathe out each minute. Now what you can see, if I just put that in purple, this is the time that exercise actually starts. If you bring that up, if you look at the difference between 0, you sort of say, okay, well 30 seconds before exercise began, let's say here, pulmonary ventilation has already increased. So this suggests that there's a sort of a neural control of our breathing. So our brain will increase breathing rate in anticipation of exercise, even though we don't necessarily need that additional oxygen. Now, as we start exercising, our breathing rate and depth, so our breathing rate and our tidal volume, i.e. the depth of breath, increase. So our overall pulmonary ventilation, how many litres of air we take in per minute, increases. So what we'll see is we'll see a gradual increase until we get to what was called a plateau that matches our muscular demand for oxygen. So one of the things that allows our body to do that is these chemoreceptors. So chemoreceptors in our blood vessels, and I think it's in our brain as well, monitor carbon dioxide. So if you think when muscles contract, they release carbon dioxide. Carbon dioxide in the blood will cause it to become acidic. So when carbon dioxide levels rise, we have to create a response to increase our breathing rate, one, to get oxygen into the system, but also to get rid of that carbon dioxide. So chemoreceptors in the blood vessels monitor carbon dioxide and hydrogen. So they monitor carbon dioxide and acidity. So when the chemical status is processed in that respiratory control center, it will affect a response. So it will increase the breathing rate and or the breathing depth. So the last point we set here, increased breathing rate and tidal volume allow greater oxygen intake and release of carbon dioxide. So the neural element of this respiratory response is our kind of brain doing this kind of feed forward anticipatory rise in respiratory rate. The chemical response is our brain monitoring the chemical composition of our blood and increasing breathing rate and breathing depth to make sure there's enough oxygen to take in to our working muscles and enough capacity to get rid of carbon dioxide. So in summary, we've kind of just done a quick sort of blast through all these key elements. You hopefully should have enough ammo to be able to explain all of the responses of those systems in that sort of shorter term acute stage of exercise. So as the body affects a response to increasing exercise demands. And that is the end.